Next type of function that we're going to look at and see how to graph are going to be called rational functions. Now, this is the generic formula for a rational function. Really, it's just you have a fraction with a polynomial on top and a polynomial on the bottom. Notice how I used n on top and m on the bottom. It's because you can have different powers of x on top and bottom. You could have any powers, so there's no way to say they're the exact same. However, in this first video, we're not even going to draw the graph of one of these, because it turns out that graphing a rational function is, 10 times harder than graphing a polynomial function. There is a lot more things going on with rational functions that you need to take into account. And so this first video is going to go over what things you want to worry about. And in the next video, we're going to put it all together to draw a graph. So the first thing that we need to worry about is the domain of a rational function. Because when we had linear functions, quadratic functions, polynomial functions, the domain was just all real numbers. So you could have any value for x and it would still be part of your graph. And that's why you don't have to worry too much about it. But for rational functions, you're almost always going to have values of x that simply do not work. And that's because we have a fraction with an x on the bottom. That means that since x changes, we might happen to divide by 0, which is something that's not possible, and that's going to mess up our graph. So first things first, how do we find the domain of one of these? Well, we look at our fraction here, and it turns out the only thing that can go wrong is dividing by 0. So we're just going to take the bottom part, we're going to ignore the top part here, take the bottom part and ask ourselves, when would this give me 0? And then we're going to solve it, generally by factoring. And in this case, we get two different values of x. But then the important thing is to remember that these are the values of x that if you try to plug them in, you would be dividing by 0, which is not possible. So these are the values of x that do not work. So then for my domain will be everything other than those two numbers. So the domain is going to be everything other than those two numbers. Okay, so that gives us the domain of one of these things here. Next thing, we can talk about a vertical asymptote. Now you may or may not recall the graph of 1 over x looks something like this here. And I want to point out that the value 0 is something special here, because on one side of the graph it just goes all the way up high, but it never crosses it. And in this case, the other side goes all the way down, again, never crossing it. So this vertical line here, the y-axis, it's a barrier where your graph cannot possibly cross it. And what it's going to do is it's going to force your graph to be in different pieces. So when we have vertical asymptotes, we're going to have our graph in more than one piece, and they're going to be going either all the way up or all the way down to some vertical line. That's why it's called a vertical asymptote. Turns out there's not much more you have to do. We already factored the bottom. We already found things that made the bottom 0, and that's where you're going to look for vertical asymptotes. The only difference is now you also want to consider the numerator, and you're going to want to factor that, in this case x plus 2x plus 1. And then what you want to ask yourself is, does anything cancel? If something does cancel, then it's not going to be a vertical asymptote. Now in this case, nothing cancels here, and that means we are going to have two vertical asymptotes. And the fun thing is about these, they're the exact same two x values you just found for the domain, but now you need the equal sign, because again, these are vertical lines, and anytime you wanted a vertical line, think back to the section on lines, it was x equals a number, and that was the vertical line there. So now these are not points anymore, these are not x values anymore, these are actually vertical lines. X is 2 and x is -1. Okay, so we do need to have those equal sign there instead of not equals. I do want to point out that if something had canceled, they would not be a vertical asymptote. They would actually be down here in the holes. So when something cancels, that's when you go down here to step 4. If nothing cancels, then you're not going to need that step 4 there. Anyways, okay, so the next thing, and usually it's going to be the last thing you have to worry about, is so-called horizontal asymptotes. And these are unfortunately quite a bit more complicated than the vertical asymptotes. In fact, we're going to break it up into 3 possible scenarios, and we're going to give you a rule for each one of those scenarios. And so that means that not only do you have to know all these different steps, you also have to know all 3 rules on just this one step. It's really unfortunate, but that's just kind of how it is. So the first is that if the degree of the top is smaller than the degree of the bottom, then you're guaranteed to have a horizontal asymptote of y equal to 0. And you can see that over here in the 1 over x graph. That would be the y equal to 0 line right there. That's your horizontal asymptote. And you can see as you go all the way to the right and left, you're going close to the horizontal asymptote, just like in the middle part, when you're going up and down, you're going close to the vertical asymptote. Now the next thing here is if the top degree, this should have said equals here, little typo on that. If the top degree equals the bottom degree, then you are going to have a horizontal asymptote, and it's going to be y equals to a number. And what number is that going to be? This is going to be the leading coefficient over the leading coefficient, which in the case of here, that'd be an over bm. So now this only happens when the degree of the top and bottom are the same, and then you take the leading coefficient of both of those polynomials, you divide them, and that will be your horizontal asymptote. We will see an example of this shortly. The third one is if the top degree is bigger than the bottom degree. In this case, there is no horizontal asymptote. So if the top is bigger than the bottom, then there's in fact no horizontal asymptote. However, I want to give a little warning here. If the top is exactly 1 more than the bottom, if that's the case, then you have something called an oblique asymptote. Some people will make you worry about this, some people won't. We will see an example of that in another video. It's just a whole extra mess, and I'm skipping over it right now. I'm just pointing out that there is something there for us to talk about. So let's look at our one example, and this part here says, find any horizontal or oblique asymptotes for this function. Well, we have to figure out which rule we're in. The top degree is 2. The bottom degree is also 2. That means we are in rule 2 here, where the top and bottom are the same. So I will have a horizontal asymptote, and it would be y equal to, the leading coefficient top and bottom are both 1, so y equal to 1 is my horizontal asymptote. Okay. Now the last thing on this video here is to mention again about what happens when something cancels out. That's when you're going to get a hole here. So notice how I just ever so slightly changed the formula of the function. Now the top is x squared minus 3x plus 2 instead of plus 3x plus 2. That's going to change the factoring here just ever so slightly. But it's going to change it in an important way where now something's going to cancel. And so whenever you have something that cancels and you solve for x, that is what your hole is going to be at. And if you want to know what that looks like, it's going to be a graph that's just going along, no problems here. And then when you get to some point, in this case 2, you're just going to have this little empty hole there. Basically, the function works no problem anywhere else, unless there's a vertical asymptote or something. It works no problem anywhere else, but when it gets to that specific point where there's a hole, it just stops for half a second, makes a hole, and then continues on as if nothing ever happened. So again, holes are things where you draw the graph like normal, and then at the place where the hole is supposed to be, you just erase a little bit, put a little empty circle there, and you're good to go.